Once more with the Mu computing stack, which I've been building up from scratch, starting with an x86 processor, a notation called subx to write x86 machine code, and then using subx to build a safe programming language called Mu. Since I built everything from scratch, there's a lot that Mu still doesn't have. And today I want to spend some time talking about a hokey way to implement images for the Mu computer. And we'll also touch upon the hokey way Mu does files. So let's boot up our computer. It runs some unit tests on startup, make sure everything is fine. And you can see that there's a sort of, I call this the shell. There's no mouse, so there's always a set of keyboard shortcuts that are available at the bottom that you can discover, and they change contextually depending on where your cursor is. The right side is a REPL where you can run commands, and it also has available a keyboard that you can read keystrokes from and a little screen that you can print things to. On the bottom left, you have a list of primitives. So there's some primitives that are for the language, just the shell language. And there's also primitives here that I think of as the syscalls for this computer. Things like drawing to the screen, and in general, any side effects we want the computer to be able to impose on its environment will come here over time. On the top, we can define functions and macros. For example, here's a macro called increment, which basically defines syntax sugar for updating a variable. And it's defined as add 1 to that variable. And adding to a variable is also syntax sugar for assigning the variable to variable plus increment. And that's made up of plus and set, which are primitives that you can see here. So that sort of gives you a quick overview of how everything hangs together. But we wanted to do images, so let's do images. So I'm going to render an image called to the screen. And what I want to do is, with the square brackets, I'm just introducing a string literal. And Mu currently supports this format for images called ppm. It's a nice simple ASCII format where you have a header, a width and a height, a dynamic range for each color, and then in raster order you just define for each pixel what the RGB values are. So we'll do that. I'll just define a simple 2x2 pixel to save time. Let's start with red. Oh, and I need to add the dynamic range. Green, one blue pixel, and then we'll make the fourth pixel yellow. And I'll draw this on the screen at starting at coordinate 8, 8. And let's start by making it 2 pixels wide and 2 pixels tall. And you can see that it's really tiny, but there's a hint of yellow and red here. Let's scale up the image, 90 pixels by 90 pixels. And now it's a lot more visible that we've drawn an image to the screen. I can now store this image in a variable. And let me get rid of the remaining arguments. And I can also now do the same thing I did before. "90 width, 90 height." Oh, and I need to give it a screen. And we get the same behavior, except now we've written this. Typing in images is a hassle, and getting data in and out of the Mu computer is still non-trivial. I don't have copy paste. So how do we do something more non-trivial? So for this, we're going to get into the file system. Well, the first thing I'm going to show is it's nice to be able to see the code for the test image, but I'd also like to be able to just render it on the left. And I can do that using some literal image macro. And now I need to change the way I define it. But notice that the moment I push the cursor out of that definition, It renders as an image on the left. To use it, I need to get past the lit image tag, which tells it what kind of thing that string literal is. And now you see that you can print it on the screen as well. Okay, so what I'm going to do now is I'm going to quit out of the new computer just for just to make a couple of things easy because they don't work right now. Let's look at the command I just ran. I run a hard disk called code.image, and I also run with a hard disk called data image. And I use this to simulate a kind of security where new programs can modify the data image, the data disk, but they can't modify the code disk. And if you look at the data disk, it's just text. There's a whole bunch of text here at the start of the disk, and then there's a whole bunch of 0 bytes. So it's a really, really simple image format. The text is an S expression. Since our language itself is Lisp, that seems like a good fit. And we have a list of global variables here. And then we have the definition of the sandbox, which should look familiar. Within the globals, we have a list of globals. And so you can see that each of these is one of the definitions you see on the left. So if you go to the bottom, you'll actually see something familiar. And so here's the definition for test image that we just wrote. One way to think about these globals is that they are the closest thing Mu currently has to a file system. And so there's a little bit of redundancy here where you see the file name here, and the file name contains this contents, which also include the definition. So I'm going to modify this disk image in place to insert a more complex image. The image I'll use is just a picture of myself, and it's 128 pixels by 128 pixels. We can't do anything too big right now. And what I've done is I've translated it into the PPM format, so it looks the same. And if you open it, you can see that it's just a list of files, ASCII pixel color coordinates, just like we saw before, but it's much larger. I don't want to be typing all this. And so I'm going to just plop that into our data image. I'll delete the existing image, and then I'll just add the new file into it. I'll save. Now let's run QEMU. And it loads up. One interesting thing here is that I had to implement dithering. So let me zoom into the picture. How do I zoom? Anyway, if you zoom in, oh, I know. You can see that it's dithered because we use regular RGB in the image, but the Mu computer only supports 255 colors. And so I'm simulating the full range of colors using dithering. And that's what I have. Thank you.